Right, hello everybody, my name is Federico, and I will talk a little bit about ontologies and relational databases. So let me do this. And so this is the program. I will start providing some background about relational databases, some very easy and quick information. I know a lot of you knows more than me about them. I'm just assuming other people are not familiar with the topic. Then I will try to describe in what they're similar and what different from ontologies, and why and when we need to work together. So very quick, there was an image here, it was a key. There should be an underscore here. Anyway, so in the relational databases, data is stored into table, at least in something we can represent as a table. Every table has a name that stands for some kind of entity, it's a universal class, and has some attributes that in a way stand for, they are the columns basically, that stand for a characteristic, you can say, of that entity. So among these attributes there is one attribute, at least one set of attributes, that is the primary key, which serves as a unique identifier for each row in the database. And you can also say that each row represents or stands for an instance or a universal class. So there, just very briefly, you can specify data type constraints. So you can say whether the data that you have to insert in a certain column must be an integer, a string, or something else, and so forth. Integrity constraints. So you can specify whether the value can be null or not, so it's kind of optional, whether it must be unique or not, whether it must be a primary key or not. But the interesting thing is that relationships are represented with relational databases. It is by using foreign keys. So foreign keys is simply a primary key of a table referenced in another table, so included as an attribute in another table. So you can see here there is a relation between the table patient and table payment because the primary key of patient is referenced there, it's contained there. So how flexible is this model? It provides some flexibility. You can express different relationships. You can distinguish, for example, identifying from not identifying relationships. An identifying relationship is when the primary key is, the foreign key is part of the primary key of the other table. You can distinguish reflexive from non-reflexive relationships. So a reflexive relationship is when the foreign key is part of the same table which the primary key belongs. And mostly you distinguish relationships in relational databases by the cardinality of the relationship. And you can distinguish at least 3 different levels of cardinality. Usually, 3 different types of relationships based on cardinality. One-to-one, one-to-many, and many-to-many relationships. This is a one-to-many relationship. You can see that because you're not imposing a unique constraint in this foreign key. And so you have the same patient can perform different payments. So patient payment is a one-to-many relationship. Same patient can perform more one payment. Another example, for example, an example of many-to-many relationship would be the relation between patient and appointment. So the same patient may attend more than one appointment, and in the same appointment more than one patient, more than one patient may be present. But this was just for some kind of providing some background about relational databases. Now let's go to similarities and differences. So some similarities are very intuitive and easy to understand. Both ontologies and relational databases aim at providing organized data relative to a certain portion of reality, at least for the main ontologies, which is machine readable. I'm talking about ontologies, but I'm mostly talking about ontology expressed using an O. So I will document saying ontology. They both provide at least good ontologies and relational databases, a clear division between the schema and the data. So instances. So for example, universal relationships on one hand, or tables and attributes on one hand, and the actual data. So the instances in case of ontologies. The way the data is organized is also similar in this way. They're both kind of provided you can represent the relationship. You can represent the way the data is organized using certain nodes and certain relationships. In the case of databases, then those will be the tables. Of course, in the case of ontologies, it would be universal. And they both allow us to impose some constraints on the cardinality of the relationship or on the type of the data in the domain. And also both can we can define in both a special relationship, a subtype relationship, even though it's intended in different ways in the two models. In the case of relational database, that subtype relation would be a one-to-one identifying relationship. What are the differences, though? There are many differences. Some are listed there. But we can summarize the thing in this. So databases are good for storing information, especially when you have a big amount of information that you have to store in a timely way. And also, they allow you to perform very specific queries on this data in a very performant way. On the other hand, ontologies are good for representing reality, of course, because they display a strong semantic expressivity. And for this reason, they also allow you to perform flexible queries, as we will see more in detail right now. So as for semantic expressivity, why are ontologies better than relational databases? One thing, relational databases do not use URI, to identify tables or relationships. So primary keys are kind of URI, but it's just for the instances. You do not use URI to identify tables and relationships, so you cannot link different tables or different attributes, columns from different databases together. And in general, relationships in databases are not given names. So the relationship is actually represented by the foreign key, and the foreign key itself can be given a name. For example, the name of the primary key in the example we had was patient ID, right? But the name patient ID does not tell us anything about the relation between patient and payments, of course. So what else? So again, we have a certain flexibility with relationships in relational databases. We can specify different kinds of cardinality, but we cannot say whether a relationship is symmetric or transitive. And so we cannot make a logic operation with this relationship, right? Ultimately, there are other points, but ultimately also, if you cannot distinguish relationships and identify relationships, if you cannot identify semantic relative relationships, then it might be hard to identify what the data in the table is about. Of course, I'm talking about machines here. You can understand what the relationship between patient and payment is about, or what the table name patient is about because they're human, and also because I use explicit names for them. It's not so easy when you're on a machine. So as for query flexibility, ontologies are much better. And so I would say more than ontology. Ontology provide an environment in which you can use languages in which query flexibility is easier for many reasons. So when you perform a query, when you look for data in a relational database, you have to know a priori in advance which is the database schema. So for example, you have to know exactly the name of the tables and all the attributes. This is not true for ontologies. You cannot perform semantic queries on relational databases. I mean, you can if you use an ontology, but you cannot without. So semantic query, for example, if you ask a relational database, provide me with all the name of the patient that suffered from tumor, it will provide you only the rows in which you find a match with what tumor. If you have an ontology, you can ask, well, yes, provide me all the patients that suffer from a disease which is a subclass of the one that knows about the word tumor, or one which is denoted with a word which is a lexical variant of the word tumor, and so on and so forth. So also, relational databases are not very good with multiple join queries. So when you ask to retrieve data, then in a way, when you have to perform a query that involves many different tables, for example, provide me the names of the patients that were treated for this disease by this physician in this hospital during this time, and so on and so forth. SQL is not very good in that. I mean, you can do it, but the performance, you will have performance issues. If you use Spark and supplement it with ontology, you can do this in a very easy way and performant way. But you can say that Spark was kind of devised for this kind of queries. And of course, using an ontology, you can reasonably create and refine queries, whether these queries are for a relational database or not. That's why they are very popular, for example, in intelligent personal assistants or natural language processor applications in general. So they help the assistant to perform tasks in an easier way. So you can ask your assistant, send an email, and the assistant will respond, which is the subject, because you can see the relation between email and subject. Well, that is just an example. So why and when do we need both? So, okay, it should be clear now why we need a relational database. When we need to handle a big quantity of instances in a timely performant way. And also when we are, our focus is only on certain aspects of a certain portion of reality. And we can provide a kind of definitive representation of this portion of reality. On the other hand, we need ontologies when we need clear flexibility, of course, and when we need to merge data that use, for example, different vocabularies. And of course, when we need our application to have deductive powers, so make inferences, acquire new information which is not explicitly stated in the source. So there are many ways, scenarios in which we might need both relational databases and ontologies. I mean, all two work together, or at least together in the same project. So there's 3 examples. Expand the semantic web to the deep web. Make inferences from big data and share scientific resources. So in this case, what you did as an example, neuroscience information framework, is provide search engines for researchers that search data in a pool with a lot of different databases, with article, other kind of data or documents, and you allow the search engine to be semantically enhanced. So you will provide to the user any kind of data which is related to the query independently of keyword match. But let's see the other 2 examples more in detail. Expand the semantic web. So what is a semantic web, first of all? Semantic web is the semantic web is a vision. It's a vision of having a web of linked data. So instead of a web full of unstructured, unrelated documents, you want a web in which all data is somehow linked in a machine readable way, so that search engines or artificial intelligence agent can understand the data documents. So there are many ways to do it. One way is by semantic annotation. So you usually use common vocabularies or better taxonomy, better ontologies that contain certain concepts that are used and shared by many different websites or software, not software, but anyway. One example we saw was, I think, DBpedia. Another example is schema.org. It was launched by Google, Yandex, Yahoo, Bing all together, right? And so you use you annotate with this term, and of course these terms you take from a common source, so you can disambiguate, but of course in the common source, the ontology, the relations between these terms are defined, so that the search engine or the personal assistant can make inferences, so it can understand new stuff that is not stated in the source, right? So you can understand, for example, in this case, that, well, Shakespeare was a playwright, then it was an author, right? Maybe you can understand that something is missing in the source. For example, there is no publishing date here, but it knows, the agent knows that one is needed. So what is the problem with semantic web? So now the semantic framework that we need to achieve, we want to impose to the web, can achieve only the surface web, but not the deep web. The deep web is the part of the web that cannot be accessed easily by search and indexed by search engines. So the point is that almost 5,000 more data is contained in the deep web rather than in the surface web. So it seems that, and also another problem is that you cannot access this data for semantic annotation in the way you can access data in the surface web for semantic annotation. So it's hard to extend the semantic web to the data in the deep web, which is data usually contained in relational databases. And this is a problem. There was a first workshop in 2007 organized by the World Wide Web Consortium on this topic, how to extend the semantic web to deep web, and so how to the data contained in relational databases. So a partial solution is this. Instead of trying to annotating or adding semantics to each single field manually for every relational database, which is impossible, we try to do this. So we know there is a certain isomorphism we saw between relational data, the database schema, and an ontology. So we try to find correspondences between the two models, or the two models, and in this way we can generate from a database schema old document using some mapping rules. And this old document is not an ontology yet, but then you can map this old document to a domain ontology, which is already linked to the semantic framework. And in this way, you can know, for example, what a table is about. You can know what kind of property and attributes stand for. And so you can know whether two databases are about the same thing, and so on and so forth. This is a simple mapping example. For example, of course, so almost every table corresponds to universal, except breach table. But I use only to indicate a certain kind of relationship between all two universals. A simple column can be mapped to the data type property, at least according to these mapping rules. And other example there. Of course, this cannot provide you with complete accuracy. Main reason, first of all, you're just squeezing all the semantics you can find in a relational databases and kind of mapping that to a more powerful sort. And so something is missing, you have to fill some gaps. Also, you can see, for example, here, simple column is mapped to the data type property. So what if you have a simple column, which is, for example, as role, right? Does it mean that as role, having a role is a data type property? Of course not. So this kind of mapping cannot handle very well. This is the moral user-mentioned distinction, right? Another example, which is more related to healthcare biomedical environment, is the following. So we collect a lot of data about patients in electronic health records. This data tells us a lot of stuff. But there is a lot of information there that is not easy to access, and we can, if we make this data understandable by machines, of course. For instance, this project was a sepsis intervention outcomes research tried to do this. They gathered 27,000 electronic health records, and they said, okay, let's try to ask something to this data. Let's ask them, first of all, which is the degree of compliance with protocols for treating sepsis in this hospital. So this data was recorded from different hospitals, as you can see. And also, let's see what is the correlation between the degree of compliance and mortality for sepsis. So, of course, they encounter some problems. First of all, presence on structured documents, or say, structured documents in the database. For example, physician or nurse notes, right? Simple free text. Machine can understand if you provide annotation. Also, physician and nurse may use different vocabularies, different terms, of course, for referring to the same thing. In different hospitals, different departments, different database schemas were employed. And another problem was that many times the data in this record was not organized in a coherent chronological manner. Why? For example, the time that was referenced in the database was not the time in which a certain medication, for example, was performed. I finished my time?
Yeah.
Oh, sorry. So just in conclusion, this was a conclusion that I find a strong negative correlation between the two things. So you can save life and money. Some conclusion, we are collecting more data than ever before. We need to store in some way. Relational databases now are the kind of tool that is more used for that. But if we wanted to transform data into knowledge, we need ontologies. So what we can do, provide new standards and languages. An example was OL2 QL, but also kind of considering ontology-related issues when designing databases. Not exactly in databases, but when we implement a database. Just an example, when we use ontology terminologies to and the terms and the concept. Not the concept, but the terms used to be not universal in an ontology for tables attributes or tables names. It's just an example. Finished. Thank
you. Could you go to slide 18? You gave an example of a simple column could be mapped to data type property. For example, if I have a table and my birth date, a table patient, and we have a birth date is a column, What kind of, for example, data property could be the mapped, the simple this kind of simple column? Because for me, sometimes the simple column could be a class.
That's true. That's the problem with this kind of mapping. That this is because, okay, this kind of mapping are not part to be performed manually, right? Kind of atomized using software. And so they have to find some rules, general rules. And the general rule is to map simple column to a data type property. And I made a data type property in an old document. And the problem is that this, of course, does not make a good distinction, a use-mentioned distinction. And of course, might be a class, but it's always treated as a data type property. There's a problem with mapping because it's not accurate, of course.
Yeah.
But this is not my ideas about mapping.
Yeah, at the same time that sometimes a simple table could not be a class, for example.
That's true. That's
could be
true.
Well,
breach tables, for example,
triple,
are definitely never class.
So, Mr. Murphy? One more question, Wally? Yes?
Yeah, quick comment on, I think in slide 8 you said that there are relations in databases, they don't have names somewhere. But this is not really precise. Most of them actually they have names. They have good names even. It's like marriage, transaction, etc. So they just objectify the.
So you're talking about relational databases?
The relations. So what we have in ontology, we have relations.
When I talk about relation, I mean so because I don't know, in relational database they use the word relation to refer to a certain thing that you can represent with a table.
A relation in a database is the table itself.
I know, but I didn't want to confuse everybody calling tables relations and then calling relation between tables relationships. It was confusing. But of course, usually the term relation is used in relational databases to name a table. But it's a different use we do in ontologies. That's why I prefer to use the term table. It's more intuitive and less confusing. That's the reason why. Of course, yeah, you're right.
Right. I would argue the primary key foreign key constraint is the relationship.
Yeah.
Well, this is the relationship.
Yes.
I think the point was that in a relational databases, the relation is the table. But it's simply because you call the table a relation, and also because of how it's implemented. But I just didn't want to confound everybody calling tables relations and then relationships, the relation between relations. That was confusing, but you're right. I mean, the real relationship is the foreign key primary key. How's that?
No.
Yeah.
No.
Absolutely.
No. Absolutely not.